Hi, this is another video about one of my electronics projects, and this one is about this thing, my experiments in creating a digital audio mixer. There's a lot of digital audio mixers out there, but none of them did fit my needs. There's some really well-known examples like the Behringer XR series. And my issue with this one is, aside that it's Behringer, is that it's lacking a lot of features until you get to the 18-channel one. I think the 18-channel one is the cheapest one you can get that supports recording more than a stereo channel from this thing. It's also huge. It takes up like 3 rack units. There's a few more compact units. Something like the PreSonus mixers. These only take up 1 unit of size, but that's still more channels than what I need, and it's still taking up too much space. Another downside is all these options are closed source products. They do exactly what it says on the box, and if you want to do anything out of the ordinary or interesting with it, it's just not possible, or you have to go connect up a Raspberry Pi and run translation software to do other control stuff, if that's even possible with the idea you have. And then I came across this thing. This is the Teensy audio shield. And this is a very simple board. It's designed to plug into a Teensy. That's the microcontroller here. As a sort of a shield. And it gives you stereo analog audio input and output. And this is not very special. You can easily make this, but the magic here is the Teensy and especially the software that's available, because the Teensy is not only a pretty cheap, pretty fast CPU. I think this one is running at 600 megahertz or something. But there's also the Teensy audio library, which makes it extremely easy to make any audio project based on the Teensy and some audio I/O boards, of which this is only an example. Using this as a digital audio mixer is possible, but it only gives you a stereo input. There's an option of connecting 2 of these to a Teensy, but that requires cutting some traces on strategic places, and it still gives you a very weird form factor and line level signals. So the obvious thing here would be making a custom PCB to have better audio I/O. And the first revision of that is this board. This is a board designed to hold the Teensy. I'm not using those pins, so I ran out of pin header here. It contains a voltage regulator here for a split 12 volt power supply, which gives me plus 12 volts and minus 12 volts, which is very useful for audio products. And it contains a lot of op-amp circuitry here to drive the XLR connectors here, which gives me some balance signals. And that is very useful for having higher quality audio and especially less noisy audio in live productions. This board already has a few weird features. Like this is designed to be 6 input, 6 output audio mixer, or 4x4, depending on how you look at it. It has 4 analog inputs. 3 of them are the XLRs on the front, and here is another jack that accepts a line level signal and is summed to mono for the 4th channel. And for the outputs, there's a stereo balanced audio output, and the headphone is a complete separate bus that gives you 2 more outputs, but it's only used for the headphones. And to make it a 6x6 mixer, there's also stereo audio for USB in and out, and that can be mixed in any way you want. And the software for this is a very simple matrix mixer without any effects. And that makes this my first prototype for an audio mixer. And this runs pretty well. except I struggled quite a lot with dealing with the noise from the switching regulators. These are very useful if you need to have a dual rail power supply for all the op-amps. But it's so hard to get it to not leak noise into any of the audio path. Especially the circuit for the audio inputs is pretty sensitive to this. After this I did a few more experiments, and that's where this board comes in. And this board basically exists because it's cheaper to get a small test board with these components made than ordering the components, and that's why I have 5 of these. And this is just for verifying a completely new circuit for receiving audio from this side and outputting audio in a balanced way, which takes one more op-amp, but it does not need a split rail power supply. This is designed to just run from 5-volt powers from USB. And this is just a simple test board that gives me a header with a line level in and out and a power header. And this is used to verify the design on a cheap board before the larger, more expensive boards are produced. And that resulted in the revision B board, which is the current one I'm working with, and this already has a bunch of mistakes that will be fixed in the revision C board in the future. This has a different layout for the op-amps. It's also a bit more compact than the original one. And it drops all the switching regulators, so it only has a few linear regulators here now. This works basically as good as the more complex dual rail 12-volt one, except that I have a design mistake on this one that make the outputs not work because all the op-amps are mirrored in the design. That's why you make cheap test boards and then copy and paste them correctly. You might be wondering why this size, why is saving a bit of size so important, and why is it 3 inputs? Why is there a PC input with mono input? And that is because this is specifically an audio mixer designed to be used at FOSDEM for a conference. And this one is supposed to run conference audio. You have 3 inputs for 3 microphones. And the first one will be generally the microphone for the speaker. And the other 2 are for handheld microphones for the audience to ask questions. The mono PC input is designed to connect to the HDMI capture box, so you can mix in the audio from the laptop from the presenter. And the XLR outputs are designed to connect up to the audio input for a camera to capture the mixed audio, at least one. And one is for doing the room audio. So this is completely a mono system. And the headphone here is just for monitoring. This will be on FOSDEM paired with most likely these. These are the wireless microphone receivers for the Sennheiser AVX microphones, which is used for most of the rooms for capturing the audio from the speakers and for the wireless audience microphones. And these all just plug into the board, and this with 3 receivers attached will make a pretty compact digital audio mixer for conference rooms. There's also this footprint here for a DECT module, and that is because these AVX systems are actually based on DECT. So one of the things I'm trying to get to work here is receiving the audio from the DECT system directly on a module that will be soldered here to mix it in as digital audio, so we can skip a lot of the analog audio altogether, which makes this even more cheap and compact. The reason why it has to be this small and why there's a random hole in the center here is because this is supposed to fit in a rack case, and only a small part of the case is dedicated to actually audio mixing, to actually mixing the audio. The rest of the space in the case is actually used for the video capture, a computer for streaming, a power board for actually supplying power to all the components, and supplying USB power to all the receivers, because they can run from battery, but not long enough for a 2-day conference. I mean, this is not a large battery, so needs to charge the receivers and the transmitters, of course. And the hole in this board is specifically because the rack case that will be used to fit all the components has some mounting posts, and having a hole here makes it quite flexible where in the case it will be installed, because it can be in the place where normally a mounting post in the case will be.
So this is the design tool made by the developers of the Teensy and the Audio Shield. And this is actually a very nice piece of software. You can just pick some modules here and make an audio pipeline for whatever you want. For my audio board, I need the I2S quad input here and the USB input, and for the outputs, the quad output and the USB output. And these modules are designed to speak correctly to multiple audio shields, and since my mixer board is compatible with audio shields, this just works. And the USB is USB. Now, to make this do anything interesting, you can decide to just hook up things and pass through audio, but this is a pretty boring mixer. What's more like the path in this mixer here is using the mixer modules, and these can take 4 channels. So if you hook it up like this, you can have any of the 4 analog inputs and route it any amount of any of these into output 1 of the audio mixer. And then the idea is that you have multiple of these and you connect stuff in parallel here, and this will become an incredible mess if you do this for 6 inputs and 6 outputs, and it will become way worse if you have even more channels. That's why I made a Python utility that just generates this directly, because it's not just the mixers here that is needed, but there's a few more things. For a single channel here, the mixer board implements the analyze, RMS, and peak. These are connected to every single channel to have information about the audio levels for any input, so that will be shown on the display. Then there is the mixer here, and it has to be 3 mixes per channel because these have 4 inputs, so these will be hooked up like this. So we can have the 6 channels, and then this is summed. This is going to a single output. Then for output levels, there is another RMS and peak, and these are connected to the same outputs. And this is the most basic single channel that is can be made in the audio mixer, basically. It just gives you a very simple matrix mixer. You usually want to do some more fancy stuff like with the biquet. This gives you a 4-band equalizer, a fully parametric equalizer. And if you want to do even more fancy stuff, there's effects here, so you can add a chorus, or there's even multiple implementation of reverbs. You can also add a few virtual inputs by using a noise generator or a tone sweep generator. And for analytics, there is the Fourier transform, so it would definitely be possible to combine these two to make some automatic EQ correction for rooms, but that's fancy stuff that's not needed yet. Another very nice thing about the audio designer for Teensy is that it understands what's actually possible to hook up. If I pick, for example, the TDM input, which gives me another 16 channels, it gives me a warning here that this uses the same pins as the quad, and that this probably won't work, or it will not work because you cannot remap the pins on this. That also means that this design is basically limited to the quad input and the quad output here. At least if you want to keep it symmetric, because there is the hex input, even the octal input, and that conflicts with output because there's a few I2S data lines on the Teensy that is shared between inputs and outputs, and the octal input uses all 4 of the I2S lines as inputs, so you cannot have any outputs anymore. Technically, it would be possible to have the hex input and a quad output, but that runs into the design issue that you need more I2C buses to actually control the codecs. The way to make an actual larger mixer with this system would be to not use the I2S codecs here, because those are all basically stereo codecs, but go for TDM. And can have TDM inputs, and there should be somewhere a TDM output, which gives us a 16 by 16 mixer. This is absolutely great, except it has one downside: getting the chips. The supported chips here are the Cirrus 8-channel codecs, and these have been end of life for quite a bit. So my plan is to, in the future, make another board that adds an FPGA on the PCB that converts more of the stereo codecs into one TDM channel to have even more signals going, because there is 32 outputs here. I think I can make a 32 by 32 mixer here, and I'm still not running out of I/O. And for the codecs I can then use the way cheaper TI PCM series codecs that are like 50 cents a piece for stereo codecs, so that is reasonably cheap to make a large mixer. But that's just future plans. The Teensy library only gives you the basic audio path of the product, and the rest of it is just implementing all the code required to control the mixer, set the state of all the mix blocks that are added in the audio path, and implement the metering. This is basically just an Arduino project, except that it's built with CMake for my own sanity. And the control method of the FOSDEM mixer here is that it's connected over USB to the PC that's in the same case, and on the USB port it has a serial port, and over the serial port it will do OSC, the Open Sound Control Protocol. And with this it's possible to set the level for any cross point in the matrix, and I still need to implement sending audio levels back over the interface, but the basic control works, and the way it's set up, it's pretty extensible because it's open sound control. I also had to add a lot of patches to the Teensy audio library itself, because the current production version of the library does not actually support having 2 of the SGTL 5000 audio codecs on the same device, because due to the chip shortage they switched from the 32-pin version of the codec to the 20-pin one. And one of the main differences between those versions is that the 20-pin one does not have a pin for selecting the I2C address, so you cannot have multiple of them on the same I2C bus. Luckily, the Teensy has multiple I2C buses, but the audio library does not have a way to specify which bus the codec is on. It's supposed to be on bus 0, but with a few patches that is easily solved. A more intrusive patch that has been added is switching over the entire library from 16-bit 44.1 kHz to 48 kHz, because modern audio pipelines, specifically the FOSDEM one, runs at 48 kHz. And this means you don't need to do any sample rate conversions on the computer side before all the live streaming stuff. This comes with a slight performance penalty. I think it's 15% slower to run at 48 kHz. And that might be a problem on the older Teensys, but since we're on the latest one, that's 600 MHz, that does not really matter, and we're not doing any really heavy stuff on the thing yet. A few more things that needed implementing is controlling the display. That will also be on the front of the case, and that should show the audio meter so you can actually see what's going on. This is just a simple loop in the code that takes all the readings from the RMS analyzer modules in the audio path and generate a nice front panel. I'm currently still dealing with the display interfering with the audio signal, but that's something that should be solvable. That is basically the current state of the project. It's far from done. There's always more features to be added, but I think as it's now, it's a very interesting board, so I decided to make a video about it. If everything works out, I will try to make a more modular version of this. One where there's a base board with a Teensy and an FPGA for doing all the audio processing and converting the signals from the codecs, and then having separate PCBs you plug in that give you more or less audio channels and the specific I/O you need for your project, and you can just have your own custom audio mixer. But that will be for a future video. Thanks for watching.